Hi, this is Physics Unit 1, May 2016. Let's start. Number 1. Which of the following is equivalent to the joule in terms of SI base units? So in terms of SI base units, the joule. So what is the joule? Joule is a form of energy, right? So in Unit 1, we have three type of energies, which is kinetic energy, gravitational potential energy, and work done. So let us just take the gravitational potential energy. Since we can take any of the three, let us consider gravitational potential energy. GPE equals to mgh, where m is the mass, g is the gravitation due to the earth, and h is the height above which any object is present. So mgh, m is mass, right? Mass is in kg. The SI unit, the standard international unit for mass, is kg. Gravity is meter per second squared, since gravity is a type of acceleration, and height is in meter. So we have kg meter square second to the power minus 2. So what answer matches with this? B. So the answer to number 1 is B. Number 2. A wind turbine generates 550 watt of electrical power for an average of 7 hours each day. So each day the wind turbine operates for 7 hours. So out of the 24 hours, it only operates for 7 hours. What is the total energy in megajoules generated each day? So each day it works for 7 hours, and we have power, and we also have the total energy. So what formula links power, time, and energy? So we have the formula: power is equals to energy by time, or work done by time, right? So the total energy would be power into total time operating. So each day, since it operates for 7 hours, we can write that the time is 7 hours, and for each hour there are 60 minutes, and for each minute there are 60 seconds. We have to convert the hours to minutes, and we have power of 550 watts. So in this case, we will get, if we do this math, we will get the energy in joules. But since we have to get the energy in megajoules, we need to introduce mega into the equation. So the value for mega is actually 10 to the power 6, and 10 to the power 6 is mega. So to add a prefix, we divide, and to remove the prefix of any prefix, for example mega or giga or tera or kilo, any prefix, we multiply. So we currently have the energy in joules, and we have to add the mega prefix. So to add mega, we need to divide by 10 to the power 6. 10 to the power 6. So the energy would come out as 13.86 megajoules, which is converted approximately to 14 megajoules. So the answer to question 2 is B. Number 3. A student applies a range of forces to the end of a copper wire and measured the corresponding new length of the wire. The force extension graph for the wire is shown. What is the maximum force that could be applied and then removed such that the wire would go back to its original length? So let's see here, from this point to this point, there is a straight line, right? There is a straight line, and then it curves out. So this point is the limit of proportionality, and this point is the elastic limit. So around 420 newtons is the maximum force that we can provide, so that it goes to its original position. Since this is the elastic limit, if we provide force beyond the elastic limit, it will not return to its original length. So for 200 newton, it will return to its original length. 300 newton, it will, let's see, 400 newton. 400 newton is the elastic, it's not the elastic limit, it's the limit of proportionality. And 500 newton is actually when it fractures. So 500 newton, we cannot use this. The maximum force that we can use from these options are 400 newton. So the answer to question 3 is C. Number 4. What is the elastic strain energy stored in the wire when extended? It is extended by 4 millimeter. So when it is extended by 4 millimeter, so 4 millimeter, milli is 10 to the power minus 3, so the units are correct. So at 4 millimeter we have 400 newton, right? We have 400 newton. So the elastic strain energy is actually the area under the graph here. So the area under the graph is actually a triangle. So the area under the graph would be E equals to half into force into del x, the extension. So half into the force would be 400 newtons into 4 milli is 10 to the power minus 3. Since we are adding a prefix, we are removing a prefix, so we are multiplying, right? We are not adding a prefix. So by calculator the answer is 0.8 joules. So the answer to question 4 is A. Number 5, the displacement graph for an object is shown. So this is the displacement and this is the time. So this is the displacement time graph actually. So which of the following corresponding velocity time graph? So let's imagine, instead of a displacement time graph, let us imagine that this is a ball. We throw the ball upwards and it goes up and it goes down. So in this way we can prove that there is always an acceleration downwards, right? If there is always an acceleration downwards, it is because due to the gravity. At first, when we throw the ball upwards, the ball is decelerating due to gravity, and when it is falling back into the ground, the ball is accelerating due to gravity. So there is a constant gravitational force being applied. So this means that the gradient of the graph will be the same. So A, B, C, D, any of them can be the answer. And then we can know that since it is a displacement time graph, so the gradient is constant, the gradient should be negative, since the initial motion of the ball is positive, and since the initial motion of the ball is positive, the gradient would be negative. So D might be the answer. And another thing, which is when we are throwing the ball upwards, we have a certain speed, right? We have a certain speed here in option D, and then the speed is actually slowly decreasing. Since the speed is decreasing due to the deceleration, it is decreasing till the point when the ball is at the topmost point, the velocity is 0. So when it is at point A is actually this in option D, and then it is again, it is accelerating downwards, the velocity is increasing. Here also the velocity is increasing in fact, but the velocity is becoming negative. At first it was positive and then it is negative. It has been negative because now the direction has changed and the direction is going in the opposite direction. So in this way we can prove that the gradient is negative and the velocity is slowly decreasing to 0 and then increasing again. The value of v is actually increasing. Since it is in the opposite direction, it has a negative value in this part. So the answer to number 5 is actually D. Number 6. A picture is hung using a wire placed over a small hook as shown. So this is the hook and this is the wire. The wire is holding the image, right? So this is T1 and this is T2. So T1 and T2 are the tension forces acting on the hook. Which of the following correctly shows the vector diagram for the resultant force T of the two tensions? So let us just rearrange. Let us take this T, this T with this T1. This is called head to tail method. Let us join the T here. So we now have T1 and T2, right? And since there is a direction, we can see that the direction is at first here and then here. So the next direction would be from here to here, right? This would become a cycle. So there would be a resultant force upwards, resultant force R or T tension which is just making forces in equilibrium. Since we know that there is T1 and there is T2, right? So we can see that there is a horizontal component in this direction of T1 and there is a horizontal component of this direction in T2. So the T1 and T2 actually cancels out the horizontal directions, horizontal components of T1 and T2, but the T1, the vertical component of T1 and T2 adds up, right? They add up. So there is a resultant force due to T1 and T2, and since there is a resultant force, there should be an acceleration, right? Since there is a resultant force downwards, there should be an acceleration since there is a force. But in this scenario, the image is actually stationary, right? It is stationary, so there should not be any resultant force since there is no acceleration. Since there should not be any resultant force, a tension of T should act upwards like this. So we can clearly see that the direction here in T and the direction here of T is the same. So the diagram which matches with this is option B. So option B is the answer. Number 7. A ball of mass m falls through a height to the ground, h to the ground. So this means that we have a ground of here. This is the ground and we have a ball here, and the height between the two is h, and we know that when the ball is here it has only gravitational potential energy and the kinetic energy is 0, and when the ball reaches in this direction and at this point the gravitational potential energy would be 0 and the kinetic energy would be maximum. So the question says that what is the kinetic energy of the ball halfway to the ground. So halfway to the ground is when it is in half the way, the half of the gravitational potential energy would be transferred to kinetic energy. So kinetic energy is basically equals to the gravitational potential energy. So kinetic energy half mv squared would be equal to mgh when it has reached the ground. But the question is saying that what is the kinetic energy of the ball halfway to the ground, halfway. So the kinetic energy halfway to the ground would be h by 2. So mg h by 2, which would be mgh by 2. So the kinetic energy of the ground would be mgh by 2. So option B is the correct answer for number 7. Number 8. A car travels at a speed of 20 meter per second due east and turns around and travels at 40 meter per second due west. So initially the car is traveling in this direction with a speed of 20 meter per second. Then the car is traveling in the opposite direction at 40 meter per second. So what is the change in speed and what is the change in velocity? So let us discuss the what speed is and what velocity is. So speed is basically a scalar quantity where it only has magnitude, and velocity is a vector quantity which has both magnitude and direction. So when the in vector quantity or velocity, when the direction is different, the sign would be the opposite. So when an object is traveling upwards at 20 meter per second, its value would be 20 meter per second. But when the velocity is downwards and it is traveling downwards with a speed of 20 meter per second, so when it is traveling downwards it is moving in the opposite direction. So instead of 20 meter per second, the velocity downwards would be minus 20 meter per second, even though the speed is both 20 meter per second in both cases, whether it is going up or down. So the change in speed, is from 20 to 40. So the change in speed is actually 20. And what is the change in velocity? So in the rightwards, when it is going in the rightwards direction, it is 20 meter per second, and when it is leftwards it is 40 meter per second. So the change in velocity would be 40 is actually a vector quantity, right? So it would be 40, and this would be minus 40. So the change in velocity would be minus 40 minus 20. So minus 40 minus 20 is actually minus 60 per meter per second. So the change in velocity would be minus 60. So the answer to this question is A. Number 9. A football is kicked across a football pitch with an initial velocity component of vertical velocity component of velocity u. The ball lands back on the pitch after a time of flight t. Which of the following equations can be used to determine t? So for example, we have the ground here. The ball is here, the ball is kicked here, and it has an initial vertical velocity of u, right? So it is kicked, it goes path, and it falls back to the ground. So what is the horizontal displacement? The horizontal displacement is this. What is the vertical displacement? The vertical displacement is actually 0, since it is going up, and then when it's at its topmost point, it just goes down. So it remains at the same vertical position but at a different horizontal position. And now in this question we are dealing with the vertical displacements, the vertical velocities, since it is clearly shown in the question. So we have S U V A T. We have S, which is displacement, which is 0. We have U, the initial velocity. We do not have the final velocity. We have acceleration, which is actually G, and we also have time t, and g is negative since the velocity is upwards but the gravitational potential energy is in the opposite direction, because the gravitational force is downwards in the opposite direction to the initial velocity. So it will be minus g, and we will have t. So the equation linking s, u, a and t is s equals to ut plus half at squared. So s is 0, 0 is equals to ut plus half into minus g t squared. So if we take t common, we will have u plus half into minus g t squared. So we would have u equals to g t squared by 2. So if we, not t squared, sorry, so this t is gone, so one of the t is gone from here and here too. We have u equals to gt by 2. So if we make t the subject, we will have 2 into u, so t 2u by g. So this is the equation for t. D is the answer for question 9. Number 10. A ball was placed on top of a compressed spring. When the spring was released, the ball was accelerated vertically upwards. So this is the spring, and when the spring is released, this ball accelerates upwards due to the force experienced from the spring, right? So if this were to be repeated on the moon, the acceleration of the ball would be so. Let us see what will remain constant in both on moon and the earth. So on the moon and on the earth, in both of the situations, the force acting from the spring would be constant, right? The force from the spring is constant since F equals to kx. So the spring constant is actually constant, right? The value of k is constant, so the force applied upwards would be constant, but the weight would increase or decrease, since we know that W equals to mg, where m is the mass, g is the gravitation, and W is the weight. And we also know that if we draw a free body force diagram, so this downwards is the weight, and the upward force is the force from the spring. So force from the spring, right? So the thing is, on earth we can do this as, we can write force Fs and earth weight of this much, for example. But on the moon, the force is same, right? The force from the spring is same, but the weight is actually lower. We can notice that this length is greater than this length. So on the moon there is a lower weight. So since there is a lower weight, is a greater resultant force, right? Greater resultant force, F resultant is equals to force from the spring minus weight. So the difference in on the moon is greater than the difference on the earth. So since the difference is greater, the resultant force is greater on the moon. With a greater resultant force, we have greater acceleration with the constant mass. So there would be a greater acceleration because there would be a greater resultant force. Since there is a greater resultant force, this is because the weight of the ball on the moon is lower, so greater resultant force and greater acceleration. So the answer to number 10 is D. That was the end of the paper MCQ. If this video helped you, please consider liking and subscribing. Thank you for watching guys, and good luck for your exams.